We will start by taking questions from the homeworks. Anybody got some that we want to talk about? I think we're up through 130 at this point, so if you guys have anything kind of in that range. Jacob.
Can you do number 123?
Yeah, 1, 2, 3. It's like we're counting here or something. All right, so we have a typo in this one. Should be pretty obvious because there was no equal sign in it. There should be an equal sign between the fraction and the 4. Probably you put that one in there without anything too hard about that. That probably wasn't the issue. But should make mention of it since we're doing it right here. First step is I'd multiply both sides by 2 to get rid of the fraction. There we go. Okay, so far so good. Next thing we want to do is I'd multiply both sides by e to the x to get rid of the negative exponent. So e to the x times e to the x is e to the 2x. E to the negative x times e to the x is e to the 0 or 1. Jacob, you good with all that? Okay. Let's move everything onto one side, and I'm going to rewrite e to the 2x as e to the x squared because of an exponent of an exponent means multiplication. We talked about that last time. So what I have now is something in the quadratic form. So I'll make a little substitution so that it looks fully quadratic for me. I'll solve that using the quadratic formula since it's obviously not factorable. There aren't two things that multiply to give me 1 and add to give me 8, or negative 8, I should say. So negative 8 squared is 64, minus 4 is 60. And 60 is 4 times 15. That's relevant because the square root of 60 would be the square root of 4, or 2, times the square root of 15. And that reduces down to 4 plus or minus root 15. But remember, we're not solving for y, we're solving for x. So let's go ahead and substitute back. So I'm going to get that. So far, so good. Last thing I got to do is get the exponent base of e out of there. How do I do that? Log base e, which is the same thing as the natural log. I got 2.06. And if I do the same thing over here, I'm going to get negative 2.06. Worth pointing out that it's not always just opposites like that, but it can be, like it was in this case. You happy with that, Jacob? If it was a logarithmic equation, I would, but this was exponential. So even though I used a log in it, it's still fine. Unless the equation at the beginning has logs in it, you should be good not to check.
If you did end up checking it, though,
Yeah, both would work. Yeah, no problem. Others. Anybody else got some that they want to talk about? This is a good one. It included a lot of concepts from last time.
Do
108. Yeah, man. Okay. What's your first thoughts here, John? Sure. Since the exponent part is all by itself, right? So you could do that here. Which log would you want to use? Yep, that would be fine. Log base 4 of 256 is 4. So x would be -3. Yeah, I point out to you that 4 to the 4th is also 256. So if you wanted to do the 1-to-1 rule here and avoid the logarithm. But either it's doing the same thing, right? 6 and 1/2 does into the other. So if you notice that 4 to the 4th is 64, then yeah, you could use that. That's how I did the log without having to type in my calculator. You know what I mean? My suspicion is you just forgot the base 4 when you typed it in your calculator. Jacob.
When you went it the other way, and you found out that 4 equals 6 first, and that kind of just do 1 minus 3 equals 4.
Then you just go straight to this step. Yep. I mean, I know that because I know 2 to the 8th is 256. That's like a computer thing. Because all the computer memories are base 2s, typically. So you know your base 2s. So I saw that. Oh, got it. Cool with that, John?
Yeah.
Okay. Anybody else? Okay. So today we're going to be finishing up section 15.4. In the first part of section 15.4, we talked about techniques to solve exponential and logarithmic equations. And what we did is we solved like contextless, just equations, just numbers that didn't have any meaning. Just equations, right? Today we're going to look at specific kind of real-life examples of actual things that exist in the world that can be modeled using exponential and logarithmic equations, and then solve those equations that we write using these models that I'll present to you. So look at like 4 of these things, I think, and just kind of do some examples, and then I'll finish us up for today. Okie doke. Okay. The first situation is loudness. Anybody remember how loudness is measured? The unit? Decibels, yeah. So the equation to find decibels is this one, where beta is just the number of decibels. And if you're a unit fan, the unit abbreviation for decibels is lowercase d, uppercase b. You're like, why lowercase then uppercase? Well, the deci prefix is lowercase d, SI unit heads. So that's how we ended up with that. I is the sound intensity. How's it going, dude? Thanks, Josh.
You're welcome. Thank you for your help on the test last week. I ended
Yeah.
up getting a 91 on it.
Good for you.
Somehow.
Yeah, that's nice.
Have a good day, though. I don't want to
Yeah.
interrupt too much.
Oh, sure. Good luck next week with the big one.
Thank you.
You're welcome. So I is sound intensity. That's measured in watts per meter squared. And then I naught is a constant. It's always 10 to the negative 12 watts per meter squared. How tall is that?
No, so you said it's always 10 to 12?
Yes, always. That's hence constant. So let's look at an example. Given the sound intensity of busy city traffic is approximately 10 to the negative fifth watts per meter squared, what is the measure of busy city traffic in decibels? Well, hopefully nobody's surprised when I want to use that decibels equation to answer a question about decibels. Right? Nobody's shocked there. What are we looking to find in this equation? Yeah, the decibels, so we're looking for the beta here. Good. And what are we going to plug in for I? The 10 to the negative fifth. And what is I naught then? Yeah, the constant, 10 to the negative 12. Okay, so we just kind of plug some stuff in here. 10 to the negative fifth divided by 10 to the negative 12th is 10 to the negative 7th. Log of 10 to the 7th is 7. And then 10 times 7 is 70. Or you could, what's up?
10 to the negative 5th.
Divided by 10 to the negative 12th is 10 to the negative, or 10 to the 7th.
Oh, yeah.
Sorry, did I say negative?
Yeah.
My apologies. Thank you. Positive 7. Thank you. Got going. You know, you get going, and your mouth is going slower than your brain is, and you know, I don't know. I don't got any excuses. It's after lunch. And probably a lot of us are kind of familiar with decibels a little bit, right? If you're a sports fan, they like in the fourth quarter, it's like, oh, look, the stadium's so loud today. They show a little monitor with a little decibel thing at the bottom. It's like this. It's as loud as a jet taking off, and you're like, yeah, sure it is. I've been to a stadium before, and it's never that loud. But okay, whatever. Everybody cool? Okay. The next one we're going to look at is the Richter scale. Oops, I don't think there's I think it's just Richter scale. What does the Richter scale measure? Yeah, it's the magnitude of an earthquake. So our Richter scale equation, R equals log of alpha over T plus B. And I'm going to abbreviate earthquake as EQ. So R is just the magnitude of the earthquake. The alpha is representing like the maximum shift in the ground level. So like when an earthquake happens, the ground is going to move up and down, right? Everybody cool with that conceptually? So the distance from normal level up or down, like the greatest distance that the ground displaces, is that alpha. So if we think about this as a function over time, the ground level is going to look like this, which is a like sine or cosine curve. And so the maximum displacement is represented by the amplitude of the curve. So I'm just going to call it amplitude here. Is that okay with you guys? And the unit we measure that amplitude with is micrometers. So that's the Greek letter mu, that U with two tails on it, or funny looking M. It's actually the lowercase Greek letter for M. Is that mu? I always think it looks like a U to me, but, you know, that's just me. The T is representing a time, so it's the time it takes for the ground to be at normal baseline ground level, go to the maximum height, up, maximum height down, and return to ground level. In the language of like a sine or cosine curve, what is that representing? The period. Yes, very good. And we measure that in seconds. And then the beta, or the B here, is like a correction factor, right? So if you're actually trying to measure an earthquake, where would you ideally like to measure that earthquake at? Where's going to be the most severe place of an earthquake? The epicenter, right? And as you move away from the epicenter, the earthquake gets less severe, right? Now, you don't know where the earthquake's going to hit. So, you know, the tool you have for measuring the earthquake may not be at the epicenter. So this is basically a correction factor that's going to correct for like the distance that your measurement tool is from the epicenter. Does that make sense there? Since the ground displacement is going to be more at the epicenter than maybe over where you're at. So it's just like a correction factor to scale your reading so it's like an epicenter reading. I don't know. Like, this is a real earth science question. I don't really know. That's probably, you can extrapolate where it is if you have a couple of these different readings. So you can see like what you read at this location, this location, this location. You can probably triangulate to where the center was going to be because it's going to move in like a circle, would be my suspicion. But I don't rightly know for sure. It could just be where they estimate the worst damage was. Okay. Who's surprised we're doing earth science today in class? We start off with some physics. Now we're going to do some earth science. A little bit later, we're going to do some chemistry, you know. It's a full day for us in the sciences here. All right, let's look at an example. The infamous San Francisco earthquake. I think we refer to it as infamous, as I suspect it's the highest magnitude recorded earthquake in the continental United States. I suspect there's been something in Alaska sitting on the ring of fire there, like in the Aleutians. It's probably higher intensity than that, but that's 7.5 is pretty bad. Had a Richter scale magnitude of 7.5. How many times more severe was the most severe earthquake ever recorded? The 1960 Chilean earthquake that had a Richter scale magnitude of 9.5. So hopefully nobody is surprised when I want to bust out the Richter scale equation to do this. Right? Pretty obvious that we're talking about earthquakes. What is the question really asking about? It's like the severity, right? Now, of these parameters, like the physical parameters of an earthquake, which one is going to describe the severity? It's like how hard it was shaken, right? Which one is telling us how much shaking is happening? The alpha, right? Like if you have a big up and down movement, that's going to be real bad for structures as opposed to like, a little up and down. Even if it's going really fast, a little up and down, it's still not that big of a deal. So we're going to be looking for alphas. Everybody's cool? Notice here we're not given any information about alpha or T or B, and we're given two R values. Hopefully it's not going to come as much of a surprise that what we're going to do is we're going to start by writing a system of two equations. Everybody's cool so far? Now we're going to think about things a little bit. So these two Richter scale measurements we have already been scaled to represent the severity or the magnitude at the epicenter, right? So because they've already been scaled, we can assume that those B values are basically either 0 or they're just the same thing. Is that, everybody's okay with that idea? Since the reading, that we got would have been something, and then we added B to it to get the 9.5, it's now representing like basically the epicenter where the B would be 0. So like they're the same B's. Cool? The other piece that we don't know anything about is the T, the period, right? So again, we're going to just assume that those things are equal. And I don't know enough about earthquake science to know if that's like a normal assumption. My guess would be like the shift up and down is maybe the same amount of time, whether it's a big shift or a small shift. That might be, might be pretty close still, close enough to where this doesn't make much of a difference to assume they're the same. Especially when you're talking about like a thing that's measured in micrometers, like might not be much of a difference. I don't really know. I'm not an earthquakeologist. Anyways, but that's what we're going to do. We're going to assume those two things are equal. So if I call these equations SF and CHI, and I want to solve this system, I would take the Chilean earthquake and subtract the San Francisco earthquake from it. I'm going to choose to do it in that order because I want to make sure that my equation equals a positive. That maybe isn't always what you'd want to do, but I'm guessing that most of the time that's probably the better option there. Cool with that? All right, notice that we would distribute the negative next. When I do that, what can I do? By distributing the negatives, what does that allow me to do? Cancel the B's, right? I have a plus B and I have a minus B, so those can just get out of there. And then notice, what do I have going on? Yeah, very good. Since we're subtracting the two logs, that is textbook quotient property. So when I apply the quotient property, the way I'm going to write it is with a division symbol, since I have two fractions inside of my logarithms, like fractions on top of fractions seems kind of like, oh, I don't know, what am I doing with that? So I'm just going to write it with a division symbol there. It's a little bit more clear what's going on. You guys remember back to elementary school on how to divide fractions? Yeah, which one do I flip? Yeah, the one on the right. So the what I remember from elementary school is that dividing fractions is easy as pie. Flip the right and multiply. Must work because I still remember it here 30 years later. So when doing that, lets me cancel the t's. Okay, now what? What do I want to get rid of next? It's really only one choice, right? Gotta get rid of that log. How do I cancel out log? So exponent base of not of the alphas, not of 2, 10, right? Yeah, that's the common log. We remember that is log base, or the common log is log base 10. So we're left with 100 equals alpha 1 over alpha 2. What is that telling us then? The alpha 2, which is representing the Chilean earthquake, is 100 times more severe than the San Francisco earthquake. Any questions on that one? It's all right? It's all right. Next thing we'll look at is acidity. How do we measure acidity? pH, yeah. So the equation for pH is that's equal to the negative log of concentration of hydrogen ions. And what's the pH scale run from? 0 to 14. And there's 3 different types of substances, right? Acids, neutrals, and bases. What pH readings represent acids? Okay, so we'll say like a set notation 0 to 7. What's neutral? 7. And what's base? 7 to 14. And then in chemistry, when you write like a bracket around a chemical substance, what does that mean? That means concentration. Very good. I've asked that question like 5 times in the past 2 weeks. You're the first person that answered it. And what unit do we typically measure concentration with? Yeah, molarity, which is moles per liter. Stretch or question?
No, just stretch.
Just stretching. Cool. All right. Very good. Let's do an example. A really sour lemon is found to have a pH of 2.2, and a bottle of bleach is found to have a pH of 10.2. Part A, what are the hydrogen ion concentrations of the 2 items? Part B, how many times greater is the hydrogen ion concentration of the bleach than that of the lemon? Well, again, hopefully nobody is surprised that we're using the pH equation for this question that has pHs in it. It's quite a shocker. So part A, we're asking about the lemon and the bleach. So we'd say 2.2 is equal to negative log of the concentration of H plus. To solve this equation for the concentration of hydrogen ion, what's the first thing I'd want to do?
Find the radius.
I need to do something before I do that. Yes, Lily.
Move the -1 to -1 exponent H plus.
Yeah, so I just need to either multiply both sides by a negative or divide both sides by a negative. So the coefficient on my logarithm is 1. And then we're going to use an exponent base to cancel the logarithm, as Elvis suggested. Which exponent base would I use in this case? 10, because it's the common log. So I'll go to my calculator and type that in. So I have 0.00631. I'm going to write that in scientific notation because, well, what's going to have more hydrogen ion concentration? A acid or a base? An acid. So I'm expecting an even smaller number when I do this for bleach, so it could get really small, and I'm just kind of preempting wanting to use scientific notation there. You know what I mean? So the steps here to solve are going to be exactly the same, right? Nobody surprised with that? So what do we have? 6.31 times 10 to the negative 11th. Woo! In part B, we ask how many more, or how many times more hydrogen ion concentration does the, well, that's a typo, right? Should be the lemon than that of the bleach. When we ask how many times greater is something, what operation are we really implying there? If I ask you how many times greater is 6 than 2, what would you answer? 3 times. How did you get that? Because we divided. So we're going to do the same thing here. We'll take the bigger concentration, divide by the smaller one. When I do that, I get 10 to the 8th. Yowzers! So that lemon has 100 million times the concentration of hydrogen ions than the bleach does. Woo! That's one sour lemon, guys. So far, so good? Okay. Last one. Is Newton's law of cooling. So what Newton's law of cooling does is it describes kind of how hot things cool down. So if you've ever like cooked a pizza roll and popped it in your mouth like a minute later and had like lava pizza roll burn the heck out of your inside of your mouth and couldn't taste anything for the next 2 days or whatever, pay attention here because we can sort this out for you. Maybe we'll figure out how long you really need to wait till you can eat your pizza roll. All right. So let's see. The T of T is the temperature of a substance. T minutes after removal from the heat source. So in the case of the pizza rolls, it's the temperature, T minutes after you take it out of the oven. Tm is the temperature of the medium. That's really talking about the surroundings. So like if you're cooling your pizza rolls on the top of the stove, that would be like the temperature of the air, like room temperature. If you're like a medieval blacksmith and you pull your sword out of the furnace and you then dunk it in a bucket of hot water or cold water, the medium there would be the temperature of the cold water, right? That process is called annealing, I believe, where you pound on the metal and then cool it down after you heat it up, and it like metal gets really hard and brittle. Not too brittle, but like you don't want your sword to bend when you hit somebody else with it. It's not a very useful weapon. You'd rather have it, break on you than bend. T naught is the temperature of the substance upon removal from heat. So that's how hot it is after you take it out of the heat source. K is going to be a constant, but that constant is specific to the substance. Which shouldn't come as a big surprise, right? Like you cook a grilled cheese sandwich and you cook some tomato soup and you put them both on the same burner at the same temperature. Which one's going to be ready to eat first? That grilled cheese sandwich is going to cool off a lot quicker than the soup does. That soup stays hot for much longer, right? You always end up burning your mouth on the soup because you're getting anxious to dip your sandwich in there. Do you like how I'm relating this all to food? This works out better when it's the period before lunch. Everyone's just like, you're killing me, Mr. Kulik. And T is just number of minutes after removal from heat. Okay. So my grilled cheese and tomato soup example is just kind of illustrating that different substances are going to cool at different rates. They have different Ks, basically, even if they're heated to the same temperature and cooled in the same room. If they're different stuff, the rate in which they cool is different, and that matches kind of what we observe in the real world, right? Okay. Let's look at our example here. A hard-boiled egg is heated to 96 degrees Celsius in a pot and then placed in a pot of 32 degrees Celsius water. I think we forgot to say water there, to cool. After 4 minutes, the temperature of the egg is 45 degrees Celsius. Find how long it will take in total for the egg to cool to a temperature of 20 degrees Celsius. Hopefully nobody is surprised when I tell you that we should be using Newton's law of cooling here. Now, if I read this story problem, it gives me a whole heap of information, right? But what piece of information is definitely lacking? Lily?
The K.
Yeah, the K, right? So what I'm going to have to do is I'm going to have to use the information here to solve K. And once I have the K, then I can do the meat of the problem, right? So when I read this, it sounds like the first couple sentences here are going to be what I need to solve for K. It's describing a very specific situation of what happened. And then later it's asking us to make a prediction. So this is kind of like a two-part problem. Okay? All right, so let's solve for K here. Let's figure out where we're going to put these. Where does the 96, where is that going to go? That's T naught. That's the temperature of the stuff when it's heated up. Where's the 16 go? That's Tm. That's the temperature of the surroundings. Good. We have 4 minutes, so that's my T. And then the 45 must be my T of T. Everybody cool? All right, well, let's solve this equation for T. What's the first thing I'd want to do? Subtract the 16 from both sides. Very good. I'm going to go ahead and simplify things a little bit at the same time. So 96 minus 16 is 80. Next up. Go ahead.
Divide by 80.
Very good. Yeah. Again, we want to get that exponential piece by itself. Very good. So we need to use a logarithm to cancel the exponent base of e. Log e is also called the natural log. For the record, if you had typed in log e into your calculator, or log base e, I should say, it does the same thing as the natural log. So if you forgot that, it's not the end of the world. And then my last step would be to
Divide by negative 4 both sides.
Yeah, excellent. I'm going to write it as like multiplying by a reciprocal, though, because I don't want to confuse myself later if I look back at this and wonder, is that dividing by negative 4 happening inside the logarithm or outside the logarithm? Because that definitely makes a big difference. So I'm going to write it that way so there's like no ambiguity about where that negative 4 is being divided. But that's just what I like to do, you know. So bless you. I do that, I get about 0.254. So this was all just doing the yellow step there. Now let's do the green step. It's asking us to find how long. So what am I solving for? Yeah, that little t. We know our K. And we're asking how long will it take to cool the egg to cool to 20 degrees Celsius. So where's the 20 degrees going? The T of T. And the medium and the temperature of the egg initially are still the same, right? So nothing to do there, or nothing changes there. It's still the same situation, right? We're just going to keep letting this thing cool in the cold water until, you know, it gets to the temperature we're looking for. All right, this is essentially the same problem as the previous one, right? The only difference is that, you know, we have a different number in front of the t, you know, the numbers are different, but it's like everything's in the same spot, variable still in the exponent, same process. So we'll subtract the 16, divide by the 80. Yes, I know I could reduce that fraction, but it's all going into my calculator eventually, so I just don't really care to reduce it. Do the natural log of both sides. And then divide both sides by the negative 0.254. Again, I'm going to write it as multiplying by the reciprocal. Now, when I type this into my calculator, I'm going to be a little bit careful here and take advantage of using all the decimal places. I'm going to use the ANS command there so that I can use all the decimal places from my previous. And I get about 11.81 minutes. If I wanted that in minutes and seconds, what would I have to do? Yeah, I'm going to subtract off the 11 and then multiply by 60. So I get like 11 minutes and about 49 seconds. So when you get home, next time you're going to make those pizza rolls, get your thermometers ready. Take a couple of measurements. Figure out that value of K, and then like you can figure out how long do I really want to get this, let this thing cool until it gets to a reasonable temperature. I probably like you know, like 120 or something. I mean, body temp is 98, so like body temp food probably doesn't feel hot in your mouth. You probably still want it a little hotter than that. I'm guessing 120-ish. You know, I'm guessing coming out of there, it's north of 200. Be my guess. And you can always like beat the system a little bit and poke some steam holes in your pizza rolls. If you know your chemistry, you know that like the energy change as water transfers to steam, there's like a huge delta K involved with that. So like there's lots of energy. That's why steam burns more than like water does at the same temperature. All right. Anyways, that's enough science corner, I think, for the day. Not that it's not interesting, you know. We're gonna stop here, given the kind of hectic week most of us have. So that allows us to do up to 138. That'll be the last of the stuff for this week's problem set. And we'll start worrying about 15.5 next time. That'll be the last section, chapter 15. That might take, hopefully, one day. If it takes a little bit more, it takes a little bit more. We'll have a review day. And then we're looking at the test, you know, next week-ish. It's cool. Best guesses, anyways. I know it's a kind of a hectic time of the year for you guys. Did I not start my recording? Oh, I had to have. Where's my thingy-majigger? I see the frame.